Good. The recording is now on. So let me just remind you that we have almost reached the end of our course. We have just one sub-module left, which is industrial control networks. We last week we missed the class of vehicular communication, so we would like to cover it on Friday. So that's why we are probably going to finish this industrial control networks on today and by Wednesday. And on Friday, probably we can finish the rest of the industrial control networks and finish the vehicular networks, and probably ask you if you have any general queries about the course. So this week, this course will be finished. That's the good news. The second thing is about this last sub-module. Well, let me just review how we have progressed throughout this whole course. We have started with the basic idea of communication networks. And at the beginning, we started with the most widely used network, which is the computer network. We tried to understand a little bit of how computer networks work, what is the architecture, where are the devices, how they are connected, and how they logically perform the interconnections between them. Then we talked about the cellular mobile networks, which is again another widely popular networks and probably going to be useful for general use. And in the third sub-module, actually, we have zoomed into some advanced as well as industrial relevant and probably futuristic kind of networks. We started with IoT. We talked about Internet of Things, and we gave you some glimpses of how IoT things are. And then we started with vehicular communication. Unfortunately, the class got disconnected and there are some technical problems. And then we today are in the industrial control network. Now, before going to talk about industrial control networks, let me just give you an idea of why this particular sub-module is very much useful for your domain. Well, it doesn't matter which branch you are from, but at one point of time, probably you will be either working in an industry or probably going to be connected with some kind of industry. Even if you are joining some software companies, you are going to work on some vertical. I hope you know that every software or other service kind of companies have some verticals that they work on banking, they're working on industry, they're working on something like that. So the closest thing that you will work with engineering is some kind of industry or manufacturing unit. Now, when you have any kind of industry, then there are a lot of things to control. And let me try to give you an idea how the industry evolved. Nowadays, we are going to talk about a lot of about industry 4.0 or 4.0. So what is industry 4.0? What are the generations of this industry and how it evolved? Just like 1G, 2G, 3G, 4G, or 5G, we also have something like generations in the industrial domain as well. So that's our next slide, or rather the first slide. So the first slide tells you about the industrial webs. So although when the industrial webs came, they were not termed as 1.0, 2.0. That is named probably a few years back. But that will help you to understand how we progressed from industry 1.0 to 2.0 to 3.0, and currently we are in industry 4.0. And people are already talking about industry 5.0 with a lot of machine intelligence and deep learning and other kind of artificial intelligence kind of things. So what is industry 1.0? Well, industry 1.0 is what we read in our history books about the industrial revolution. That means prior to that, we had something like products made in home settings. But during the industrial revolution, that happened something around 1780s or so. There were mechanizations. That means there were machines which can do a lot of similar jobs quite quickly. And they were having the power from the steam turbines. And one such example is like a weaving loom. So earlier, we all had something like the textile industry, which was only a cottage industry. But with this industrial revolution, it became a mainstream industry. And similarly, many other industries boomed during this. But you have to remember that there was no electricity at that time, so everything was steam powered. But mechanical engineering has started to flourish, and there were a lot of machines which could help this industrial revolution. So To some extent, the first industrial revolution was can be largely accounted for the mechanical engineers as well as some civil and metallurgical engineers as well. What happened 100 years later? If you see the industrial revolutions, the second industrial wave came almost 100 years later, when there was electrical engineering. So I should probably give the credit to the second industrial revolution to the electrical engineers, who came up with better methods of electricity production, electricity transmission, and electricity usage. And they helped in lot of modernization of machines. And it was possible to generate a power at a place and use the power at a different place, which was not the case in Industry 1.0. In Industry 1.0, you have to generate the power where the machine is, but in Industry 2.0 helped to separate the power production units apart from the factories. And there was again another brilliant idea of the mass production, which cannot be particularly accounted for any branch. It was like many branches combined together. But again, mechanical engineers kind of played a vital role. So we had something like assembly line, like we had conveyor belts, we had assembly line kind of ideas. So the factories were managed in a much better way. So we knew what are the processes one after another. They had designed in a logical fashion, and they were doing like a serial kind of thing. But still, in Industry 2.0, it was like all manual. So it was not automatic. So there were machines, but they could not think anything of their own, and their control was always on the same part. That means you have a machine on or off switch that is connected to the machine itself. So you have to go near the machine and then turn it on or turn it off manually. So that was the case in 1870s. So it took around 100 years, and this time the computer science and the electronics people contributed a lot for Industry 3.0. So what they did was they separated the control unit of these machines or assembly lines or something from the machines themselves. So you can now have remote controls, and you can have some degree of automation. So robotic hands and other things that came into the picture. Now, not much ago was the Industry 3.4, and it took around 50 years to come to the next industrial revolution. Now, this next industrial revolution is not only about better software or something. We have something like called cyber physical systems. What are cyber physical systems? Well, we have something like a fully virtual kind of environment which we can simulate in a separate place, which is not in the factory itself. So we have cyber systems, we have physical systems, and we have a communication between them. So control, communication, software, electronics, computer science, everything came together, and we formed a big network. So what was the case in Industry 3.0? We didn't have something like a quality control which can be maintained throughout all the branches of a company, but that is possible now, because we can have a central control and we can control all the branches of an industry, and that's something like Industry 4.0. In Industry 5.0, as I said, that people are already doing research, and they are thinking about like artificial intelligence and deep learning, where probably machines can produce machines themselves. So that's something like a futuristic idea. Now, where the industrial control network stands, like I have talked about 4 industrial waves, and that is probably pretty easy to understand. But where does this industrial control network, or ICN, which is the topic of today's discussion, stands? Of course, it comes after Industry 3.0, and it realized Industry 4.0. So let's go to that slide. Now, in industrial control network, let us first try to understand what are the information that we are dealing with. Well, this information is not about the speech or the music files that probably we share commonly via our personal networks. For example, a computer network realized through internet, or a cellular mobile network, or maybe a Bluetooth network when you are sharing with your friends. So it's not that kind of information. It's kind of information that is relevant to the industry. So there are 3 such type of information. First is the control information. Second one is the diagnostic information, and third one is the safety information. Now, of course, from these terms themselves, you understand what they probably do. The first thing is control information, which probably is used for some kind of control of actuators. And then there is diagnostic information that you probably get something from a sensor. And then there is some safety information, which is something like alarm or critical. To give you an example, if you are working on a coal mine, then there is obviously a cutter which is working in the mine. So at which rotation, at which speed and at which direction you have to drill, that is a control information that should pass from a control station above the mine to that drilling machine. On the other hand, the drilling machine has some sensors, like how heated it has already become or how deep it has already gone. So those kind of information are diagnostic information which should be sent back to the control unit, so that based on that, further control information can be sent. And there are some alarming situations, like there might be a methane gas breakout or carbon monoxide gas breakout, which should be we should trigger some alarm, and probably everybody should be evacuated. So those are safety information. So that can be obtained from some carbon monoxide sensor or methane gas sensor, which might be embedded to the drilling machine, or maybe it might have a separate network under the mine. So this is the difference between control information, diagnostic information, safety information. Now let's see what are the details. Well, the control information is passed always between instruments and controllers, and they have real-time and deterministic requirements, because they deal with actuator positions or fuel tank levels or fluid flow or drive speed, this kind of information. So they should be done on real-time basis. You can't say that, okay, your file is getting downloaded, so I will tell you next minute that how much you need to drill. By the time the probably drill is broken. So they have a very much real-time and deterministic kind of requirements. On the other hand, the diagnostic information is generally it is generally collected. Sometimes it is acted, but sometimes mostly it is not acted out. Like what is like the amount of drilling done throughout the day in different hours, or current drawn by a motor, or temperature of a bearing. So these are the diagnostic information that are generally collected. Sometimes they are only collected, sometimes they are acted upon as well, but they are acted through the control information only. Now, in the middle of the paragraph, there it's written that they require temporal consistency and minimal data loss. Well, what they mean is they don't, most of the time they don't have a real-time requirement. Like you need to update the database right now, maybe after a few milliseconds, it's fine. But they require less amount of data loss, like that should be recorded accurately. And finally, we have a safety information. So the safety information is used to implement critical functions. That's just what I said, like a carbon monoxide breakout or something. Now they require very, very high reliability, because if you are going for a false trigger, then it's obviously not good for an industry. And as they have high reliability, sometimes they are realized with an altogether separate network. Just think about the 911 service. The 911 service is realized with cellular mobile phones, but they generally are done on the higher priority. So they are treated as a different network from the normal phone calls which are being carried by cellular phones. So what the safety information can be? Well, it can be shutting down of an equipment, or it can be shutting down of protection circuits and so on. Okay, now this is giving you some glimpses of how an industrial control network deals with different kind of information. Let us now try to compare with some enterprise network, like for example, an internet in an office, side by side. So the next slide is about that. That is, if you look at a network in a company, and if you look like a software company, and if you look at a network in a factory, how they're different. So the same solutions does not exist in both the cases. So if you are working for TCS, then probably you will be dealing with a different network. If you are working on the ground site of Alstom, then probably we are going to require a different network. So that's that difference is going to be described in the next class. Sorry, in the next slide. So here are some parameters which I have noted down on the left-hand side, and based on that, we can compare the enterprise or conventional network with the industrial network. That means the network, say for example, in a software company and the network in a real-time factory. So the first thing is the primary function. Of course, the primary function is completely different. Well, in industrial network, we generally don't use for internet surfing. Mostly we use it for control of the physical equipments. Like it can be a drilling machine, it can be a motor, it can be a pump, it can be a sensor, anything. On the other hand, in conventional network, we generally have the basic idea of like data processing and transfer. Then the second one is the domain. Well, the domain of industrial is naturally the manufacturing, the processing kind of things. On the other hand, in the conventional networks, we generally have enterprise networks like in business centers or data centers, or in corporate worlds, like in a hospital or something, or maybe in a home environment. Now, the third point is hierarchy. Now, what is hierarchy? Well, in case of hierarchy, hierarchy means how many levels the network have. Now, generally, the enterprise networks have small hierarchies. Like if you remember a WLAN, well, every computer can be connected to a hub. So they don't have many different hierarchies. On the other hand, in industrial network, we generally have deep hierarchies. We will explain it either in today's class or the next class. Now, the failure severity is obviously high in industrial, because if the data transfer is not successful, then they can cause a havoc. Similarly, the reliability is also very high in industrial, but they are low and moderate respectively for the conventional networks. Now, the round trip times, what we mean by that? Round trip time is when you are probably sensing something through a sensor, and then it goes to the control station, and then some information comes back. It's like you are probably facing some difficulty in operation, you are reporting it, and then the boss says, okay, you should probably change this way. So that kind of information flow to and fro is called round trip time. Round trip time is very, very low for the industrial networks because you need immediate action. So that's why you can see that the requirement may be as low as 250 microsecond. At least it is always less than the millisecond barrier. On the other hand, in enterprise networks, we don't mind having a delay of around 50 milliseconds or so. Now, again, the determinism is very, very high in industrial networks. And but when we consider the data composition, well, the data composition is completely different. In enterprise networks, we are dealing with big files, database updates. So we have very large and aperiodic. That means they are not coming regularly. Sometimes you are downloading a big movie, so you have large chunks of torrent files, sometimes nothing. So that's the conventional. On the other hand, in industrial networks, they're always like small packets, but they can be periodic or aperiodic. Like if you are having a sensing kind of thing or trigger which triggers some alarms, then they're aperiodic. But if you are reporting the temperature every 5 minutes, then it is periodic. But how much data you require to record the temperature? It's very few. So the packet size is very very small. Well, the temporal consistency, that means the gap between the packets, that should be uniform for the industrial networks. Like if you are giving some instructions, so you should give it in a periodic fashion. On the other hand, in conventional network, that is not required. That means if you are downloading a big file, it doesn't matter whether the part 5 comes before part 3. But in industrial networks, it is probably not allowed. Finally, the operating condition in conventional networks is very clean, generally not very hazardous. On the other hand, in industrial networks, it is hostile, hazardous. There might be different kind of chemicals. There can be heat, vibration, dust, and probably a lot of other issues. The air can be not as clean as in a home environment, or there are what I should say, like there are chances of short circuit and many other things. So it is much more hazardous in industrial network. Okay. Now I was talking about hierarchy. So in the next slide, I will try to talk a little bit more about the hierarchy. So let's see the hierarchy of the industrial network, and let's see the hierarchy of a commercial network. Now let us try to understand the right-hand side figure first, which is much easier. Like suppose we are talking about a wide area network or WAN. Now wide area networks are connected to the side backbones. That means the big optical fiber cables which probably encompass the whole city. And then we have local subnetworks. For example, let us take Durgapur city. Now in Durgapur city we have a WAN, and then we have say two set of cables. One set of cables is covering zone Durgapur A zone, and the other set is probably Durgapur B zone. Just for example, there might be more than two. Now in A zone, there are many campuses, like CMARI is one campus, NIT Durgapur is one campus. So they have their local subnetworks. So this is how the commercial networks operate. On the other hand, let us have a look at the picture on the left-hand side, where we're talking about industrial networks. Now, in an industrial network, at the lowest level, we have field equipment networks. Now, these field equipment networks can be a series of temperature sensors which is connected to a PLC, or a programmable logic controller. Then above that, there is something control network. Then above that, there is some application network, supervisory network, and external connection. So there is a lot of such things. But this hierarchy is not clear right now from this abstract figure, I understand. But it will be clearer when we will discuss some specific examples. Now, one such now this is one issue. I will probably keep it for rest. And then the other thing is, we were talking about failure, like failure severity. Now let us talk about the failure severity, like why the failure severity is high in industrial network. So I'll show this slide. Well, this slide shows three cases on the right hand side. Of course, the bottom picture is about Bhopal gas tragedy. Can you identify the other two? Like, I hope people are there and you have your chat box. So can you identify the other two pictures? They are some kind of industrial disaster. And the slides are kind of old, so it has nothing to do with Ukraine. So I'm looking at the chat box, try to figure out what these two pictures are, apart from the Bhopal gas tragedy. No, Mohit, I already said that it is not related to Ukraine. And Chernobyl is a very sparsely populated area, but the picture on the top is not from a sparsely populated area. But one thing is, you are right that it is related to something kind of nuclear disaster. But it didn't happen in Chernobyl. Any other answer? The right side picture, yes. Mohit, now you're right. It is the Fukushima disaster, which happened after the tsunami, and there was a Japanese nuclear disaster. And the right hand side picture is from India again. And that was one of the very big disaster during the COVID times. And it is related to some COVID vaccine. Okay, so still no answer. So I'm telling you that it is about the fire that broke out in Serum Institute of India, which was one of the biggest vaccine providers. I hope you know what vaccine they produced during this COVID. So everybody knows about these two vaccines. And I also took a dose of that vaccine. So with this picture, what I wanted to show you is that whenever there is an industrial disaster, that has an effect which is not only felt right, yes. So which not only is its coefficient. So actually this disaster that happened in Serum Institute of India, there was a fire breakout, and that probably delayed the vaccination drive for several months. So you can see that any industrial disaster does not have only immediate effect, it has a prolonged effect. For example, the Bhopal gas tragedy, it has a prolonged effect of many years. Like Mohit said, Chernobyl, it is having a disaster for 30-40 years. Probably the effect is felt even today. So the industrial control network should be very, very robust, and any failure can lead to say the least, the damage of the equipment, and then probably the production is lost. Then bigger disasters like environmental damage and the loss of reputation, and then obviously loss of life, which is the probably the biggest thing that can happen. But they are all related. So that's why I was talking about like the failure severity or reliability, like why the reliability is very important in industrial control network, and why the severity for failure is felt so much. Okay, so now I go back again to the different slides, and there I talked about the temporal consistency. I said that we need equal gap between the data packets for industrial networks. We also said that the round trip time should be small. So that means the delay, that means you send something and you get a response, the delay between them should be very low. Also, the delay jitter, jitter means variation. So the delay variation should be also minimum. Like if you're expecting 20 milliseconds, let it be always 20 milliseconds. It should not be sometimes 0 milliseconds and sometimes 40 milliseconds. It's not going to be good in that case. Although the average might be same, but still it is not good. So we both want both the delay to be as low as possible. Also, the delay variation should be as low as possible. Why so? Let's talk in this slide. Well, the thumb rule is like why we need instant transmission or processing or response. The thumb rule is very simple. Like the response time should be less than the sample time of data being gathered. Like if you are taking the temperature of something and you are taking the temperature after every 5 minutes, then if you take a value and respond to that value after 5 minutes, then there is no point, right? Because already there is, and again, another data. So you should work on the new data itself. So that's the basic thumb rule of engineering. It's common sense, but sometimes people forget common sense. So we have to put it in a thumb rule like this. The second thing is the response time, which is of the order of millisecond. And sometimes it can go down to microsecond as well, when there is very high speed rotating kind of things. I was talking to one of my colleagues, and they were like dealing with something like he was in the aerodynamics lab of IISc Bangalore, and they were dealing with some high-speed rotor blade of an helicopter. And they said, we are dealing with bullets, like if a high-speed thing is going on, and if there is a small thing breaks out, it just comes out at a speed of more than bullet. And if you are there, then you are instantly dead. So you need to be very cautious with those high-speed motion kind of things. The second point that we want to discuss on this slide is that the delay variance. Well, the delay variance or the jitter is also critical, because you see, when you have a variance of delay, like sometimes the response is obtained within 10 milliseconds, sometimes 20, sometimes 30, that's not good, because you have a control loop. If I have electrical friends, probably they understand it better. But in any case, there is a control loop, like you give some signal, you get some actuator activated, and then you give some sense thing back and it goes back. So it's a continuous loop kind of thing. That whole loop gets affected with this jitter. And also, when you are considering it in a digital form, then also you need a fixed gap, because otherwise the digital sampling and the signal processing, everything goes in jeopardy. And finally, I was talking about the data packet and periodicity and temporal consistency. So those things I just want to describe a bit more. Like the data packet size is always very small. For example, a few bytes for an alarm. How many bits you require? Probably 20, 30, 40 bits max. And there might be the periodicity is about, I already described, but I still describe once again that data can be periodic or data can be aperiodic. Periodic means it is coming regularly. When regularly? When you are monitoring the status of a sensor, whether you have turned the seat belt on or not, like every 15 minutes the car checks, for example. On the other hand, event triggered means there is something, some breakout, some fuel loss from the tank, some gas leakage, something like that, or short circuit. So those are the events which trigger some kind of data. So there are two type of data in industrial control network. One can be regularly coming status monitoring. The other can be emergency kind of data. And sometimes it is not always related with some safety. It can be turning off and turning on of some machine as well. Finally, we talk about temporal consistency. Well, the temporal consistencies is like we need the timestamps and synchronized clocks. Like what we mean is that we need to track it so that in the time domain, so that probably we can handle the data better. Okay. Now let us talk a little bit about the ICN modules. And here I will end today's class because we are on the 10th slide and we have hardly 20 slides. So I think we can finish the next few slides in the next class. Okay. In the industrial control network, we have this many modules mostly. Well, we have generally 3 levels. I hope you remember this diagram. If not, I go back. I talked about, where is the hierarchy? Okay. I talked about the field equipment network, controller network, application network, supervisory network, external connection, and so on. Now let's try to see with more practical examples. Like there are some device levels. These are field devices. These field devices might be humidity sensor, for example, which might be put in an agricultural field to sense how much moisture is there in the field, which probably gives you an idea which at what time you should sow the seeds and so on. And there can be other kind of devices as well. So there are a lot of devices in the device level, which are field devices. Now these field devices generally does not have a control circuit of their own. They are generally connected to a PLC or programmable logic controller. So that's why this layer is known as PLC layer or control layer. And these PLCs are connected via some switches where the data transfer is done with switch. Switch you already know, we have talked about in our computer network course. And at the top layer, we have something like a human machine interface, HMI. HMI is like a software which is controlling everything. Like you can have SCADA or something, that kind of software we can control the PLCs. So there are in the field actual devices. These fields are connected to some programmable logic control network, which might be on some lamp post or something. They are connected to the data cable through switch, and these data cables come to a computer which is in the central office. And in the central office, in that computer, there are some software being run, which is taking the data from the PLCs and based on that giving the PLC information, which is again fed back to the devices. So this is how a thing works. Like I gave an abstract idea and then I give a practical example. Like suppose we have these industrial equipments which are in an oil rig. Now these oil rigs are connected to the programmable logic controllers. Now what this PLC one could like compare the measured flow to the set point, controls the pump speed. So on the similar way, the PLC2 is also going to do the same, but we have some different actions as well. Like we can controls the flow through the valve to match level to set point, and here it is about the pump. Here it is about the valve and so on. So there are 2 set of programmable logic controllers which probably takes care about 2 different actions, and then they are connected by a switch. So this is a switch, and this switch goes to the SCADA server, which is a supervisory control and data acquisition kind of system. And this SCADA system is connected to some human machine interface where there are some screens where probably you can see the output of these devices which are used to control. And then there can be some heterogeneous network as well. Like this switch is controlling the PLCs because these oil rigs are at a fixed position. But we can have some temperature sensors which are connected with some remote transmission unit as well. So in a wireless manner, we can also connect. So we can have wireless connection, we can have wired connection, finally going everything. So this blue part is in the office. On the other hand, this is in the field. So this is how they they are connected together and they are controlling some industrial control network. So this is what I wanted to discuss till today. And here we'll stop the recording, and tomorrow we'll finish this. Tomorrow we'll